Hello, my name is Daniel Hudson, and I'm presenting Physics 2212 Lab 5, Faraday's Law. In this experiment, I dropped a bar magnet through a roll of aluminum foil. By doing so, the bar magnet accelerated slower than it would have dropped outside of the aluminum foil tube, which is due to the force, the induced force of the induced magnetic field. I recorded the drop with a smartphone to determine how long it took the magnet to fall through the tube, and then I modeled the falling of the bar by taking those initial measurements. The fundamental physics principle involved is obviously Faraday's law, which states that the induced electric voltage can be calculated from the magnetic field by the cross-sectional area, which is flux. And if you take that derivative over time, then you can get the voltage. That voltage gives you it can help you calculate the current of the aluminum toy using Ohm's law, and then the magnetic field due to the dipole, which I used to calculate Faraday's law, is shown as the third equation. And finally, magnetic force is the final thing to calculate, is just the current crossed with the magnetic field, and that's the force of the tube on the magnet, which is what slows it as it is dropped through the tube. Here are the quick experimental results. After 5 trials, the average time for the magnet to fall through the tube was 0.25. Computational model is shown here. On the left is the calculation of the magnetic field due to the magnet. On the bottom left is the change in flux over time. So this is by applying that changing magnetic field to the area of the tube, we can calculate this change in flux. On the right, we can take that and put it into a current, and then apply it to a force, which is done on the magnet by the tube. Well, it's reciprocal, so they're both applying equal force on each other. And this is what's used to complete the model. You can see here's the model results. As it's falling, you can see as it starts to slow out near the bottom, and then it sort of bottoms out for a little while. I think there must have been a slight miscalculation mistake, because it should end around 0.25 is when the slope hits about 0, and there's a quick little drop at the end there, but I think most of the right half of that graph can be excluded. So we can determine that the model's time in the tube is roughly about 0.25, or a little bit bigger than 0.25. So it's slightly larger than what I got in real life, but pretty close. And so just some final follow-up questions. What happens if we reduce the resistivity of the conductor? Well, by reducing the resistivity of the conductor, we can reapply Ohm's law, which states that the voltage is equal to the current times the resistivity. So if we have a smaller resistivity, then our current actually increases. This then goes into the calculation of the force, because force is current times the length of the tube, and cross that with the magnetic field. So if we increase the current, we end up getting an increased force on the magnet by the tube. This increased force causes the magnet to fall slower through the tube, so we would end up getting a stronger and stronger time. So if you were to reduce the resistivity to essentially 0, you could get the time to go increase extremely. But now what happens if we were to cut holes into the tube? This would be the exact opposite situation. This would reduce the current in the tube by removing the length of the tube, by removing the size of the conductor. So here I can explain that better. We reduce the area that the tube takes up, so our flux is smaller, which decreases the voltage. This decreasing in voltage and a similar resistivity is a smaller current. This smaller current then has a smaller force on the magnet, causing the magnet to fall faster through our tube. Okay, there we go. Thank you for watching this video, and best of luck in physics.